Welcome to lecture number 12 of our course on high performance computing. In the previous lecture, we have seen or started to look at the software side of the picture. Other than the programs that we write, there is a fair amount of important and interesting software which helps to determine what happens when our programs execute. And in the slide which we are using to represent the computer organization software side of things, you'll remember that the hardware is the base, and I'll direct you to look at that slide. So the hardware is the base on which the software organization of the system is built. That's why at the bottom of the slide on the software organization of the computer system, we have a box labeled hardware, and that box contains, as I said, the ALU, the processor, the I/O devices, bus, and so on. Above this, we understand there are going to be various software components, because it is within the hardware box and only within the hardware box that there are going to be hardware components. The rest of the organization of a computer system is going to be through the software components of the computer system. So in the diagram on computer organization software that we were using in the previous lecture, and which I would now request to come up on the screen, we have the hardware box at the bottom of the screen, and above this we have various software components of the activity on the computer system. So you'll notice that we have various entities which are either in white or in yellow, and it is only the hardware that we have been talking about in prior lectures. So we are now using the term process to refer to programs in execution, and there is the very key operating system, the key component of the software of the computer system, which is represented closest to the hardware in this particular diagram. Now the different processes or programs in execution, when they require functionality from the operating system, will do so by calling function-like entities known as system calls, which are interfaces into the operating system. And last time we saw some interesting system calls. For example, there is one of the system calls known as fork, and if a process calls fork, then the effect is that on its behalf the operating system does something through which a new process comes into existence. And the original process we henceforth refer to as the parent process, and the new process we refer to as the child process. And in fact, both the parent and the child process execute the same program. They are two processes which are now associated with the execution of a single program. Some of the processes that we had shown were clearly operating system related, because they are shown in yellow, which is the operating system color on this slide. Okay, now in the end of the previous lecture we were discussing how the yellow parts of this computer organization software slide, such as the parts over here, must be capable of doing very privileged operations on the hardware. Now the ordinary white processes will use all the instructions that we saw: add, load word, jump register, jump and link, and so on. But as far as the operating system is concerned, there may be a need to use some very privileged registers or some very privileged other capabilities that are present in the hardware and not made available to the user programs. So what we saw in the MIPS-1 instruction set architecture was clearly just a subset of the actual MIPS-1 capabilities. A MIPS-1 processor is capable of executing all the instructions that we saw, but in addition, some additional instructions that would be included for the use of very privileged programs such as the operating system. Okay? So basically the complication that we have now is we understand that such privileged instructions might be included in the instruction set for specific use by the operating system and special programs of that kind. But when a program that you or I write runs as a process, and that process makes a system call, which is definitely a possibility. As we saw, I can write a program which calls fork or exec or sbreak or open, close, read, write. So many system calls that are very useful to programs that you or I might write. When my program is executing inside a system call, it is executing in the yellow part of that diagram, and it is executing a piece of code which might have to make use of privileged instructions. And that is not something that I should be able to do in a program that I write, because if I can write a program which can execute privileged instructions, then I could also take the privileges that should be available only to the operating system. So this is a subtlety that has to be addressed very carefully by the hardware. So we need to understand what happens when a system call takes place. Clearly it's not just going to be like a function call. In a function call there is the need to save return address and all that complication that we saw, but ultimately there was just a control transfer. Whereas in the case of a system call, there is very clearly the need for a control transfer, but also the need for some kind of a privilege elevation, a change in the status of the process which is making that control transfer. Okay. So in order to achieve this, what is done is that processor designers design the hardware of the processor so that it can operate in either of multiple modes of execution. At the very least there would need to be at least 2 modes of execution, and as you'd imagine, one of the modes is going to be available and it's going to be an ordinary mode, which is the kind of mode in which instructions of the kind that a program of yours or a program of mine might require, the ordinary instructions that we have seen of the MIPS1 instruction set. So the hardware will be designed so that it is either executing in this ordinary or user mode, or in a more privileged mode called the system mode. So at any given point in time the processor is executing instructions and it is in either the user mode or the system mode. Therefore, if it is in the user mode, it can execute the ordinary MIPS1 instructions but not the privileged instructions, whereas if it is in the system mode, it is capable of executing the privileged instructions. What will happen if I write a program and I include a privileged instruction in the program? Now when I write a program and it runs as a process, the process will be running in user mode until I try to make a system call. So if my process is running in user mode and it tries to execute a privileged instruction, the hardware will notice that the processor is currently in user mode and it will give an error violation indicating that an attempt was made to execute a privileged instruction, and I will find out that my program is not allowed to do so. Whereas if the program is executing in the system, is executing in the operating system or executing inside a system call, it will be in the system mode, and if it executes a privileged instruction while in system mode, the hardware will know that this is a allowed execution of a privileged instruction. How does the hardware know whether it's in user mode or system mode? You remember that there are special purpose registers inside the hardware. We talked about processor status register. So it is conceivable that one of the bits of the processor status register indicates what mode the processor is currently executing in. Now I have indicated that, so the current mode of a processor might be indicated in a processor status register. Remember that the processor status register, like the program counter or the instruction register, are special purpose registers within the CPU used by the control hardware. In this bullet I have suggested that hardware has to be designed with at least 2 modes of execution, a user mode and a system mode. A processor could be designed to have 3 or 4 modes of execution, in which there is some refinement of the different kinds of functionality that might be available in the privileged mode. But for our purposes, we will just assume that there are precisely 2 modes: the ordinary mode, which my program or your program runs in, and the privileged mode, which is the mode in which the operating system programs or operating system code executes. Therefore, as far as the mechanics of a system call is concerned, we understand that if my program executes, if I write a program which makes a system call, then in order to execute in the system call, my program has to change mode from user mode to system mode. And there is no other way that my program can execute the system call, because the system call code is basically going to contain privileged instructions. How can this change of mode take place? The answer is this will have to be done explicitly by the execution of an instruction. And as we saw, the MIPS1 instruction set had an instruction called syscall, which we can now interpret as system call. And if my program executes the syscall instruction, then essentially it switches mode from processor mode to user mode before transferring control to the appropriate system call. So the syscall instruction can be used to switch modes in order to transfer control to one of the specific system calls, and not arbitrarily just changing mode from user to system. So it's a control mechanism for changing from user mode to system mode for the sole purpose of executing in the system calls. You'll notice that this is an interesting instruction, syscall, because it is an instruction that does transfer of control. It clearly must save return address, because ultimately after the system call is executed, control must be transferred to the instruction after the fork in my program, after the system call in my program. But more curious than that, the syscall instruction itself cannot be a privileged instruction. It has to be an ordinary instruction, because the syscall instruction has to be permissible in ordinary user programs. So this is an instruction which is an ordinary instruction which has a side effect of changing from user mode to privileged mode. It does other things as well, such as saving return address and transfer of control to the appropriate system call, the beginning of the appropriate system call, and possibly some of the other complications that we saw as far as function calls are concerned. So this is essentially what happens in a system call. You'll notice that there is a need for hardware support as far as system calls is concerned. So it's conceivable that there are processors that exist today on which Unix cannot be ported just because they don't have features of this kind. It may be possible for somebody to attempt a port of the Unix or Linux operating system to such a processor, but it may end up being either extraordinarily difficult because of the lack of hardware support, or it may end up being not possible at all. Right? So in the design of processors, the architect must take into account certain requirements of the operating system, and we see that the linkage between the operating system and the hardware is possibly closer than we thought. In designing the hardware, in designing the instruction set, the computer architect does not just take into account the requirements of ordinary programs, he must also take into account the very, very specific and privileged requirements of the operating system. Okay, now moving right along, I am going to refer to the process lifetime. I've used the word lifetime before. We talked about the lifetime of a piece of data as being the elapsed time, or the time interval between the time that it ceased to exist and the time instant that it ceased to exist, and the previous time instant when it came into existence. Some pieces of data have lifetimes which are the lifetime of the program in which they come into existence. Other variables, other pieces of data have lifetime which is related to a function call. Others have lifetimes which are related to explicit points in the program, for example, the time interval between malloc and free. We can also refer to the lifetime of a process, by which we would mean the time between the termination of the process and the creation of the process. So this is what we would refer to as a lifetime of a process, the time between the termination of the process and its creation. We know that the process is created by a call to fork, and a process terminates due to a call gracefully on a call to exit. And therefore, the lifetime of a process could be quite clearly calculated, or quite clearly measured. Now, while a process is in execution, it might be interesting to keep track of how much time it has been in execution. In other words, the amount of time associated with that process at that instant. So it turns out that in Unix systems, as we have seen, at any given point in time, a running process is executing either in user mode or in system mode. It will be executing in user mode if it's executing the instructions of your program. It will be executing in system mode, for example, if it is executing a system call as requested by your program. Therefore, if I talk about the lifetime of a process as this time interval, some components of that time interval are going to be spent executing in user mode, and some components of that lifetime are going to be spent executing in system mode. Therefore, I could actually talk about the time in user mode, or the CPU time spent by my program in user mode, as well as the CPU time spent by my program in system mode. And possibly the sum of these two would give me some idea about the total amount of CPU time that my program in execution took. And these might be interesting values to know, because we talked about how the objective of taking this course was to try to improve our programs. And one aspect in which we may want to improve our program is by reducing the amount of time that it takes to execute. And therefore, I would be talking about trying to reduce the total CPU time used by the process, which is my program in execution. And while it might be possible for me to control the amount of time in user mode, it might not be possible for me to control the amount of time in system mode without reducing the number of system calls that my program makes. So if we make sure that the number of system calls that our programs make are as required for for achieving the functional requirements of the program, then the second aspect is outside of our control. All that we can do is to rewrite our program to improve the amount of CPU time spent by our program in user mode. Therefore, this is an important distinction. And as I have indicated over here, on Unix or Unix-like systems, there are facilities provided through which you can actually find out the amount of time spent, the amount of time, CPU time spent by a process while the process is running. In other words, one could make calls to those facilities from within the program and then print out the values of the amount of time, total CPU time spent, or the total amount of CPU time spent in user mode, total amount of CPU time spent in system mode, to get some idea of what your program is doing in terms of the amount of time it has spent. Okay. Now let's go back. In talking about computer organization, the software side of things, I have talked about two programs. One is the operating system, and strangely enough the other was the shell. And I had suggested that the operating system is very special, whereas when I talked about the shell I said it is just another program. We have seen two examples of shells. I talked about CSH and BASH, and you could, if you have access to a Linux or a Unix system, you could read more about either of these shells. But just to convince you that a shell is just another program, we will next try to understand what a shell does, and in fact write pseudocode for a shell, a very simple shell. Okay, so what does a shell do? Now you will recall that shell is the word that is used for command interpreter. Command interpreter. So a shell takes a command from the user and it interprets or causes to get achieved that command. We had examples where in response to the request from the shell for a command, if I typed in PS, which is the command that can be used to get status information about the different processes running on a system, then the shell would take the information from me and it would cause the PS program to execute, and I would see the output from the PS program on the screen. So basically that's what a shell does. So we see that what a shell does is it prompts the user for input, then after the input is typed, it prompts the user for a command, and after the command has been typed in, it obviously reads in the command, understands what the command is supposed to do, and then achieves that command. And after doing that, it prompts the user for another input. So just putting this down, one thing which the shell has to do is prompt the user to type in a command, and that's actually quite easy for us to do. You know that you could write a program which could do this. All that you have to do is to print the character % to standard output in some sense, if the standard output is related to the console. So this is actually very easy to do. But the first thing that a shell has to do is print the shell prompt on the screen. That's what I mean by prompting the user to type in a command. After this, it has to wait for the user to type something in, and it has to read in the command. What's involved in reading in the command? The command would have to be read into a variable or an array of some array of characters. So an array of characters would have to be declared. The command would have to be read into that array of characters using any of the standard I/O functions that you might be familiar with, such as scanf or something like that. After this, the shell would have to understand what this command is asking for. For example, in the case of PS, understand that this is a command which is requesting that the PS program be executed. And after having done this, the shell would get the command executed. So the next thing that it has to do is to get the command executed. And having done that, it repeats this process. So basically the shell is this infinite loop which prompts the user to type in a command, reads in the command, understands what the command is asking for, and gets the command executed. Okay, now we do need to understand a little bit more about what's involved in all these things, all these steps. But let me just zero in on two aspects of what the shell is doing. And one is understanding what the command is asking for. Now, this is not a trivial step in the operation of a shell, because there are actually many different kinds of operations that one could type in response to a shell prompt. One thing that one could do, as we saw in the case of executing a program, is to type the name of an executable program file. You'll recall that if I had a program in C called program.c and I compiled it using GCC program.c, then I get as output a file called a.out, the default name, which is an executable or an object file or a machine language equivalent of the C program. It is a file which contains the machine instructions and various other things which are equivalent to the program.c that I wrote, and I can cause this to be executed. So in response to the shell prompt, if I type the name of an executable file, then that is a request to the shell to actually run that executable file. But there are other things that I could type in response to the shell prompt. For example, the shell may have been written so that the shell has certain specific commands of its own, which do not correspond to program files. For example, most shells will have their own exit command, and the purpose of the exit command is for the shell to terminate. Therefore, exit is not the name of a program, it's not the name of a program file, but exit is the name, is just one of the commands that the shell can inputs and understands that this is a request for the shell itself to terminate. And you ask yourself, what sense does it make to ask for a shell to terminate? And let me put it to you this way. Let's suppose that I am running on a computer system, a Unix system, in which by default the shell that I am given is CSH. Right? So by default, when I get the shell prompt, I am getting a CSH shell prompt. Now what if I want to actually change to the bash shell for the session that is going on right now? I know that bash is the name of just another program from the previous slide. So I know that somewhere out there is a file called bash, which is an executable a.out equivalent. It's not called a.out, its name has been changed to bash, but it is of the same format. It is an executable object file containing machine instructions, which is the shell program. Therefore, if I wanted to switch from CSH to bash, I could actually run the bash program. The effect of running the bash program is that the bash shell is going to execute. It might have a different prompt. For example, the prompt might be $. Subsequently, when I type a command, the command will be interpreted not by CSH but by bash, because I am now executing the bash shell. Now if I looked at the output from PS, what would I see? We saw that in the previous instance when I typed PS, I got information about all the processes which my program is running. So I expect that there will be one line for PS itself, as we saw last time. There will be one line for bash, because that's the shell that I'm currently using. But as you would imagine, there will also be one line for CSH, because CSH is also still in execution. So there will be 3 lines in the output at least. Now at this point, if I'm happy with having experimented with bash, I may want to get rid of bash, and the way that I can do that is by typing in the command exit. Remember, this is the bash shell prompt, and exit is now a request to exit from bash. What will happen? The bash program will exit, and I'll be left with the C shell command prompt. So just like this exit, there could be a lot of other shell commands, and therefore when you type in a command, you could type in the name of any executable file, such as a.out or bash, or you could type in the name of any shell command. And one can learn more about the different shell commands by reading the manual of the particular shell that one is interested in. Okay, now there are also some other complications which, as you use shells, you will be aware of, but all of that functionality must go into understanding what the command is asking for, and that's a non-trivial operation. But for a very simple shell, it could just be reading in the command and calling the appropriate executable file. Okay, now the next issue, which is of some importance, is how can the shell get the command executed? For the specific example that we have, the user wanted the a.out file executed. So how can the shell cause a.out to be executed? Now we have seen only one mechanism that's available to change the memory image of a program, and that is the exec system call. So one possibility for the shell is that it could run, in order to achieve a.out, the shell could actually execute an exec indicating that it wants its new memory image to be that associated with a.out. And that would cause the memory image of the shell, let's say the bash image, to change, as we had seen in the previous class, to the memory image of a.out. So this is now the text segment of a.out. And as you'd imagine, this is not what we want to do. because the effect of the shell execing a dot out will be that the shell itself ceases to exist. We no longer have a process which has as its text the instructions of that shell. That has been overwritten by the instructions of a dot out. Therefore, in order to get the command executed, the shell cannot just call exec, the exec system call with the name of the file that is to be executed. Rather, it will have to subtly create a process using fork, as we have seen in the previous lecture, and then within the child process do the exec of the required executable file. And this is a sequence which we had seen in the previous lecture. Therefore, that is in effect what the shell would have to do in order to get the command executed if the command is the name of an executable file. Okay. If the command is just a shell command, then the shell will contain instructions, will have been written to contain instructions which will achieve the required effect, such as exit. So, the bottom line is that the various steps within the shell, and this is a program that you or I could write, will be making many system calls. For example, to prompt the user to type in a command, one could think of using printf. If you actually analyze what printf is doing, printf is just the name of a function or something like that, but ultimately it calls a system call which is capable of outputting onto the screen. The screen is an I/O device which is shared among possibly many processes, and therefore access to that I/O device must be shared through operating system functionality, and ultimately a system call must be used in order to cause the output to take place to that I/O device. Similarly, in order to read in the command, the shell will probably use something like scanf, but that's just the name of a function or something like that in a library. Ultimately, that function is going to make some kind of a system call which will have the capability of transferring data from the keyboard, which is a hardware device, into a variable in memory. So, even for the read command, a system call will be involved, but the person writing the shell does not have to know anything about the system call involved in outputting to the monitor, or the system call involved in reading from the keyboard. The person writing the program may just use printf and scanf. In understanding what the command is asking for, it's possible that no system calls are required, but as we've just seen, in order to get the command executed, both fork and exec may be required. Again, if the command is a shell command, then there may not be the need for fork or exec, but if it's the name of an executable file, then conceivably both fork and exec will be required. The bottom line is, we can see that in order to implement this functionality, one can just write a C program making the appropriate system calls as and when needed, and this program is just an ordinary program. It's an ordinary program which will request the operating system for the key functionality as and when required using the system call mechanism, which at this point we have somewhat understood. So, we understand what the distant system calls are as well. Okay. So, at this point we will now formally start looking at the operating system in more detail. I have mentioned that the operating system is software that manages the resources of a computer system. Clearly understand that the operating system is entirely software, it is not hardware. The requirements of the operating system may have affected the way in which the hardware is designed, as we have seen. It's conceivable that in designing an instruction set architecture, the architect may have had to include certain instructions in order to properly support Unix, but all the same, Unix itself is just the software. So, it is a software that manages the resources of a computer system. What do I mean by the resources of a computer system? I am going to list four types of resources. First, there is the CPU time, and just a few thoughts on this before we proceed. Now, we have a situation where we have a computer in which there is one CPU, one main memory, a bus, and many I/O devices. The key here is that there is only one CPU, and on this there could be many processes executing. However, there is only one CPU, and if there is only one CPU, there is only one program counter. In other words, only one instruction can actually be executed at a given point in time. That's under our current understanding of how the hardware works. So, what then does it mean to have many programs in execution at the same time or concurrently? Very clearly, the operating system is managing the CPU time. It's allowing, let's say, one program to execute now, and after some time allowing another program to execute. We'll look into some details of that a little bit later. But we have to view the CPU, or the time of usage of the CPU, as being one of the hardware resources that has to be managed by the operating system. There's nothing in the hardware to manage the CPU across processes. The hardware does not even know about the existence of processes. The hardware just knows about instructions and the execution of instructions. Right? So the management of CPU time is going to be an important functionality of the operating system. Secondly, I've listed main memory. What do we know about main memory? We know that as far as main memory is concerned, if there are many processes in execution, then all of those processes must have their programs present in the main memory. Right? So as far as main memory is concerned, I will have the memory image of each of those programs present. That's the only way that each of those programs could potentially be executed within the CPU, because its instructions have to be fetched from main memory, not from elsewhere. Therefore, very clearly, the operating system must be involved in the management of main memory. We have seen that there is one component in the CPU called the MMU, which assists in something called address translation. But address translation alone might not be the whole story as far as management of the main memory is concerned. Address translation might be the key lowest level link in the chain, which must be implemented in the hardware, which is why it is represented by the box called MMU. The rest of memory management, the rest of the management of main memory is something that must be of importance. Next, I have listed I/O devices. Now this is a slightly more complicated story, because I have not talked in detail about I/O devices yet. This might be the right time to do that. You will remember that I/O devices include devices for input and devices for output, and we have used many examples. For example, we understand that one of the important mechanisms for input is the keyboard. There's also the mouse. On the output side, there is the monitor. But there are other kinds of devices. For example, we are aware that I've talked about the fact that there could be disk memories, hard disks inside a computer system. Is that an input or an output device? So I'll put it somewhere in between. The notion of a hard disk. You may have CD drives, VCD drives, whatever, in a computer system. These are other examples of I/O devices. There may be a printer. A printer is typically an I/O output device. There could be scanners. These are all examples of I/O devices, but there are others as well. For example, what about the network interface card that is present in your computer? I'll refer to this as an NIC. Many of the computers that you have today are connected on networks, and the connectivity is provided through a piece of hardware which might be called the network interface card. It could be an Ethernet card, it could be something else, or it could be provided through a wireless interface. But this is just an example, a network interface card. And one may have to view the network interface card also as being an I/O device, since input and output from this particular computer does take place through the network interface card. So when we talk about I/O devices, the range of hardware that could be included could be fairly vast, different kinds of functionality. And we may not be able to address issues related to all of these, and it may not in fact be pertinent to us. We will want to concentrate on those I/O devices which play a specific and particular part in the day-to-day execution of the kinds of programs that we might execute. And that might in fact just be restricted to the hard disk. So among all the I/O devices, we may just restrict our attention to one or a small number of these in our discussion. Now, last but not least, the operating system will possibly have to be involved in the management of software resources. We have already seen in our diagram of the computer organization, the software side, that there are many processes in a computer system, many programs in execution represented by these software entities or these software resources called processes, which require the operating system to intercede on its behalf. We've also seen that the operating system is involved in the creation or the termination or the manipulation of these processes. Therefore, from the operating system perspective, the processes and other objects of that type are software resources that have to be managed. Therefore, in studying about the operating system or in discussing the operating system, we need to look at each of these four one after the other to understand how the programs that we write and execute are affected by the operating system in terms of the way the operating system manages CPU time, main memory, I/O devices, or software resources. So we will need to go through these one by one, and I am going to start with main memory. So this subtopic is what would normally be called main memory management. It's the story about how the operating system is involved in the management of main memory. And for future reference, the specific example which I am going to use with something which is fairly popular among the kinds of operating systems that we are dealing with is something known as paged virtual memory. Okay, now let me just remind you that we have seen that there is a need for address translation. Where did this need arise from? We saw that on any particular computer system, one particular computer system, there could be many programs in execution. Each of these programs is written or compiled to assume that it uses addresses from 2 to the power of 32, from 0 up to 2 to the power of 32 minus 1, and that there could be many such programs in execution at the same time, and that therefore if all of these programs had their memory images in memory at the location specified, then one program would certainly be able to affect another program, not only by the fact that their instructions would be overlapping, but that if I knew that if this is the memory image of my program and this is the memory image of your program, and I know that your program has an important variable at a particular memory address, then I could modify. Your program thinks the value of the variable is 1. I could change the value of the variable to -1 by just changing the variable from my program. So there's a need to protect one program from another program in terms of its memory image, and that's why we figured out that address translation was a mechanism to do that. The idea of address translation was that the addresses 0 through 2 power 32 minus 1 that the compiler assumes will be associated with the program in execution will be viewed as being specific to that process or that program in execution, and that prior to actually being sent to main memory during program execution, the address would be translated to an actual main memory address, and this translation would be done by a piece of hardware called the MMU. Okay. Now we didn't talk about how this translation was going to be done, we just said that it would be done by the MMU. Now if you think about it a little bit, in order to translate one address into another address, one will have to have the base information on which the translation is to be done. In other words, one will need a table of translation information. If there is a table which tells the MMU what address 0 relating to process 0 means as far as main memory is concerned, then the MMU can just change address 0 into that address by doing a lookup in the translation table. Therefore, this is a useful idea to have, the idea that address translation can be implemented using a table of translation information. What will this table contain? This table will contain, for each address in the range 0 to 2 power 32 to 0 to 2 power 32 minus 1, it will contain the corresponding address in main memory to which the translation is to be done. Okay, now this of course raises an issue, and that is the issue of the size of the address translation table. At this point I should possibly remind you that we had talked about virtual or artificial addresses, and the addresses generated by the compiler are virtual addresses as opposed to physical or real main memory addresses. And that the address translation process done by the MMU basically converts a virtual address into a physical memory address or a physical address. Okay, now if this translation is going to be done using an address translation table, we have to think a little bit about how big that address translation table is going to be. Let's spend a little bit of time thinking about that. Okay, so our current concern is the size of the address translation table. Okay, now as I reminded you, the address translation table contains a mapping from virtual addresses to physical addresses. It tells the MMU how to translate each virtual address into the corresponding physical address. And one way that this could be done is, as I said, through a table. This table is going to contain, for each virtual address, the corresponding physical address. So in the diagram that I show you here, I have actually shown you a table which contains a lot of physical addresses. How many physical addresses? That depends on how many virtual addresses there are. So let's suppose that there are 2 to the power 32 virtual addresses. Then the first entry in this table will tell you how to translate virtual address 0 into a physical address. Similarly, the last entry in this table would tell me how to translate the address 2 power 32 minus 1 into a physical address. And how will it tell me that? It will tell me this by containing the corresponding address. For example, suppose virtual address 0 is supposed to translate into physical address 100. Then the first entry in the address translation table will contain physical address 100. Similarly, if address 2 power 32 minus 1 is supposed to translate into virtual address 2 power 32 minus 1 is supposed to translate into physical address hex FFFF, then that's what that entry in the address translation table would contain. In other words, what I'm doing, the way that I use this table is, if I want to translate an address I is some value between 0 and 2 power 32 minus 1, then all that I have to do is I have to index into this table using address I, and that will tell me how the virtual address I is supposed to be translated. Right? For example, if it's supposed to be translated into 64, this entry in the table will contain the address 64. Therefore, we can calculate what the size of this address translation table is going to be using this idea. The idea is essentially that I have a table which tells me the physical address for each possible virtual address. The table need not contain both the virtual address and the physical address. It need contain only the physical addresses, and I can, by looking at the ith entry in the table, I will know the translation for virtual address I. Okay, so how big would this table be? Let's suppose for the moment that we do what I just described, and I have an entry in the table for each address that I have in terms of the virtual address space. In other words, I have one entry in this table for each byte address. Okay, so if I have one entry in this table for each byte address, then the size of this table would be the number of byte addresses, which is 2 power 32, multiplied by the size of a physical address. And up to now we've been assuming that the size of addresses is 32 bits. We'll continue to make that assumption. What's the size of the table? The size of the table will be the number of entries, which is 2 power 32, multiplied by the size of each entry, which is 32 bits. So this is the size of the table. How big is this? We know that 2 power 30 is what we call the gigabyte. I'm sorry, it's capital G. Therefore, 2 power 32 is going to be 4G. 32 bits is 4 bytes, and therefore the value that we see, in other words 2 power 32 multiplied by 32 bits, is the equivalent of 16 gigabytes. 4G multiplied by 4 capital B, which is 16 GB. And once again, remember that G in this context just stands for the constant 2 power 30, which is why I could write 4G and multiply it by 4B and come up with 16 GB meaningfully. So the size of this translation table is going to be 16 gigabytes. Now this is a bit of a concern, because in passing, when I talked about the different kinds of memory which are available in a computer system, I talked about main memory, we talked about registers, talked about cache, but not in enough detail to include it in this list here. Then we talked about other possibilities like hard disk, DVD, CDs and so on. And I also gave you some idea about how big each of these would be. I had indicated that, for example, just think about the MIPS1 registers. We know that the MIPS1 contains 32-bit registers, which means that the size of the registers in the MIPS1 is something like 32 multiplied by 4 bytes, or 128 bytes, which is nowhere close to this. I had also mentioned in passing that a typical size of main memory for a very healthy machine today could be something like 4 gigabytes. The desktop or the laptop that you have may have 4 or less gigabytes. In other words, this translation table is so big that it won't even fit into main memory. We know that the size of hard disks is significantly bigger. For example, many of you will have hard disks which are 300, 500, 250 gigabytes in size. Therefore, this translation table is so big that the only place we could store the translation table on the computer system would be on a hard disk, which is not a very promising beginning, because we wanted to use the translation table as a reference for the MMU, in other words, a part of the hardware, a part of the CPU, to do translations of addresses before the addresses went to main memory. And if a reference to hard disk has to take place for every address translation, we understand that the hard disk is significantly slower than main memory, then this is not going to be a very good mechanism. Therefore, it is not feasible to do things along these lines. That is the bottom line. Our concern about the address translation table is real, in that if we were to use an address translation table in which there is one piece of address information for every byte, then the table would be so big that it would not be a feasible mechanism for address translation. Now, what if on the other hand I were to assume that there is an entry in the table for each word address? So, rather than for each byte address, I have a translation entry in my address translation table for each word address. How is this going to change things? Now, rather than having a separate address translation table for byte 0 entry, for byte 0, byte 1, byte 2 and byte 3, there will be a single address translation table entry for bytes 0 through 3. In other words, the size of the address translation table is going to come down by a factor of 4. So, the size of the address translation table will be 4 gigabytes. This is a little bit better than it was before, because now the address translation table could fit into a large main memory, but it would occupy all of main memory, and therefore once again does not seem like a feasible option, because remember, our starting point was we want the need for address translation arises because there are many programs resident in main memory at the same time, and if all of main memory is full of the address translation information for one of those programs, then the system does not work. So, clearly we need something else. Okay, now let us look at a larger grain possibility. Let us suppose that we started off by assuming there was one address translation entry for each byte and saw that that was not feasible. We then said let there be one address translation information for each 4 bytes and saw that that too was not workable. Moving in the same direction, let us assume that there is one piece of address translation for each 256 bytes. In other words, for all the bytes between byte 0 and byte 255, I have just one entry in the address translation table. So, the size of this is going to be 1/256th of the size of the original table that we had. And what is 16 GB divided by 256? The answer is, just remember that G is 2 power 30 and 256 is 2 power 2, 4, 8, 16, 32, 64, 256 is 2 power 8, I believe. Then what you end up with is 16 is 2 power 4. So, on the top we have 2 power 34, on the bottom we have 2 power 8. You are left with 2 power 26, which is 64 M. M is 2 power 20 and 64 is 2 power 6. So, that works out correct. So, the reason I went through this example is so that you will get used to the notion of dividing one value which is in this notation by another value in the same notation. Typically the powers of 2 cancel out, so the calculations are easy. So, under the assumption that there is one entry in the address translation table for each 256 byte units of the virtual address space, then the size of my address translation table is only 64 megabytes. And therefore, I could comfortably include many such address translation tables into main memory for the many programs that are in execution at a particular point in time. So, we seem to be moving in the right direction, but the key towards moving in that direction is that we need to associate with the address translation table entry a very high granularity of addresses, not a single byte address, not a single word address, but a single virtual address for at least 256 bytes, consecutive bytes in the virtual address space. Okay, so the size of the address translation table was a concern to us, and we saw that the means of reducing the size of the address translation table was by not managing translations on a byte basis. In other words, not a separate entry in the address translation table for each byte address, but at some larger granularity, such as one address translation table entry for each 256 bytes of the virtual address space. Right, so, this seems to address the problem of the size of the address translation table. Now, this does not fully address the problem that we have, because you understand that all of this translation is supposed to be done by the MMU, and by using this idea we have reduced the size of the address translation table to 64 megabytes, which I argued was feasible in the sense that I could have many such tables present in main memory. But if the address translation table is present in main memory, then in order to do the translation, the MMU will have to make a main memory reference, which is going to take 2 orders of magnitude more time than we hoped it would take, because we were including the MMU inside the processor, hoping that the translation could happen at processor timeline speeds, not at memory timeline speeds. So this is still a little bit away from being a feasible solution to the problem of how to manage main memory. And when we continue from this point in time in the next lecture, we will understand a little bit more about how this scheme can be made to work. Just to remind you what we have been looking at in today's lecture. In today's lecture, we have formally understood that we need to understand the operating system from the perspective of 4 aspects of its functionality: how it manages CPU time, how it manages main memory, how it manages I/O devices, of which we may look at the specific example of the hard disk, and how it manages software resources on the computer system, such as processes. We also looked at the mechanism that is provided for safe transfer of control from a process into the operating system through the functionality of the system call, by providing inside the instruction set and inside the hardware the capability for execution in multiple modes, one of which is a privileged mode in which only privileged instructions can be executed, as well as a user mode ordinary instruction through which an ordinary user process can switch to the privileged mode in order to call a system call. And this instruction in the MIPS1 instruction set was our syscall instruction. So with this, we are all set to formally look at how different functionalities of the operating system affect the programs that we execute. Thank you.